I'm going to sketch a proof of how we can start with a normed vector space and construct a complete normed vector space that in some sense contains the normed vector space we started off with. This essentially shows that any normed vector space can be completed. In particular, the construction I'm about to sketch can be used to start with Q and get R. The basic idea of how you go from Q to R and how you complete a normed vector space are quite similar. So the situation we are in is we have a normed vector space V, but it could possibly be incomplete. What that means is there could be a Cauchy sequence, xn Cauchy, such that there is no limit. So the question is, we have to somehow add points to the vector space V in order to make sure that every Cauchy sequence converges to a point in V. Now, what is the point you would add corresponding to this Cauchy sequence which is not converging? Well, what could be more natural than representing that particular point that we need to add by the Cauchy sequence itself? So this might seem like an extremely bizarre way of doing it, but if you think about it for a moment, it's extremely natural. We need to complete it by adding points, and these points correspond to Cauchy sequences in the original space V that do not converge. Therefore, we add that Cauchy sequence itself as the limit. Now, one issue that might arise is that there are many Cauchy sequences that converge to the same point. If you had a vector space V, normed vector space V, there could be multiple Cauchy sequences that could converge to the same point. Furthermore, we need to sort of define a norm for this point that we are adding. So let's do this step by step. First, let's take care of the norm by this simple lemma. Let V be a normed vector space, and xn in V be a Cauchy sequence, Then norm xn converges. Okay, so the proof of this is rather trivial. This proof immediately follows it is immediate from absolute value of norm xn minus norm xm is less than or equal to norm of xn minus xm. From this, it is immediate that this sequence norm xn is a Cauchy sequence, and therefore it must converge because R is complete. Okay, so what this lemma suggests is that once you add these Cauchy sequences, let's suppose you denote, you are going to essentially define the norm of this Cauchy sequence to be nothing but limit of norm xn. Okay, that's what this lemma suggests. Now, another question. We have this new vector space V that has some bizarre elements. They are Cauchy sequences. What is the zero element? Okay, now the zero element should correspond to Cauchy sequences that converge to zero. But there are many of them, and which one do you choose? Well, we are going to choose in some sense all of them. So let me now formally state the definition of the completion, and I will sketch a proof that this definition is in fact makes sense. I'm going to define various things, and they may not be well defined. I will sketch a proof that all the things that I'm claiming are well defined are indeed well defined. Completion of V. Okay, so the setup is, let V be a normed vector space, denote by CS of V the Cauchy sequences in V. So what we are doing is we are taking all the Cauchy sequences and putting it inside a basket and calling that basket CS of V. Now, as we have observed, there are multiple Cauchy sequences that converge to the same point. So we need to identify certain Cauchy sequences, and the perfect way to do it is to use equivalence relations. We define an equivalence relation on CSV as follows. The sequence xn is related to the sequence yn if and only if xn minus yn converges to 0 in V. Okay? The fact that this is a Cauchy sequence is, the fact that this is an equivalence relation is utterly trivial. So I'm not even going to bother mentioning that anymore. Okay? Now, the crucial definition. Define the completion of V, which I'm going to denote by V closure as a nice mnemonic. Define V closure to be the equivalence classes. The equivalence classes of CSV under this equivalence relation. Okay. Now I'm going to denote an equivalence class like this. Okay. Now we need to define the operations under CSV that make it a vector space, and those operations are rather straightforward. We define the equivalence class of xn plus the equivalence class of yn to be, as you can guess, xn plus yn, the equivalence class of xn plus yn. Similarly, scalar multiplication is dealt with in an exact same way. The equivalence class of C times, the element corresponding to C times the equivalence class of xn is nothing but the equivalence class of cxn. Okay. We also define the norm of xn, the equivalence class of xn, to be limit norm xn n going to infinity. Okay, now there are a number of trivial checks that need to be done to ensure that we have not done anything illegal in this definition. Okay. The fact that it's an equivalence class is trivial. I'm going to leave it to you. First, we have to show that these operations that we have defined, xn plus yn and cxn, they are independent of the representative. So suppose we have xn is related to un and yn is related to vn. Okay, suppose we are taking two distinct representatives of the single equivalence class box xn. Now we have to show that the output that you get, this xn plus yn, actually there is no necessity to put a box. We have to show that this xn plus yn is related to un plus vn. That will show that our operation is independent of the choice of representative. But that is easy because xn plus yn minus un minus vn converges to 0, because xn minus un converges to 0 and yn minus vn converges to 0. Therefore, xn plus yn minus un minus vn converges to 0. So the addition operation at least is independent of the choice of representatives. In an exactly similar way, we can check that the scalar multiplication is also independent of the choice of representative. Now, once you have these operations showing this V closure is a vector space is just a long but easy check. You have to check each and every one of the stupid axioms of a vector space. Okay, so we have at least constructed a vector space of Cauchy sequences, or rather equivalence classes of Cauchy sequences. We have defined a norm. We have to now check that in fact this is a norm. So again, these are all straightforward easy checks. Let me just do a few of them. Suppose you have that the norm of a particular equivalence class is 0. Okay. Now this will happen if and only if norm xn converges to 0, because that's how the norm in this complicated space of equivalence classes was defined. You just take norm xn and take limit n going to infinity. Now this will happen if and only if xn converges to 0, right? And this will happen if and only if this box xn is 0. So this chain of equivalences proves that the norm of an element in our bizarre space V bar is 0 if and only if the representative, that is box xn itself, is 0. Okay. Now similarly you can show that it's rather easy to show that a norm of C box xn is equal to mod C norm of box xn. This is an easy check. Okay. Now coming to the triangle inequality, what we have to do is we have to consider norm of box xn plus box yn. But the operation means that this is nothing but norm of box xn plus yn. Okay, which is nothing but limit norm xn plus yn. That's the definition of the norm in this vector space, which is less than or equal to limit norm xn plus limit norm yn by the triangle inequality, which is equal to norm of box xn plus norm of box yn. So this shows that the triangle inequality is satisfied by our definition of norm on the space V bar. Okay. Now consider the map F from V to V bar. Okay, and the map is given by X maps to, as you can guess, the constant Cauchy sequence XXXXX. I should put a box around it for the definition to be 100% precise. Now this map is obviously injective. And it is equally obvious that it is norm preserving. That is, the norm of X is the same as norm of box of X, which is obvious. Okay. Linearity is straightforward. Linearity is also straightforward. I want you to do it. It's just a 30-second check. Okay. So what this shows is that this map F is an injective isometry from V onto f of V. Okay. So what this shows is that V is sitting inside V closure as an isometrically embedded copy. So essentially we have extended the space V to this larger space V bar or V closure or whatever you want to call it, and V is sitting in there exactly as a copy, that is in the guise of f of V, in a different disguise. It's sitting in there as f of V. Now we still have to show that this bizarre space V bar is actually a complete normed vector space, and that is going to be taken care of by the next lemma. The next lemma relates density and completeness. Okay, what it says is the following: let V be a normed vector space. I'm just going to abbreviate it as NVS, and W be a dense subspace. So it's a subspace of V whose closure is equal to V. Okay, if every Cauchy sequence in W has a limit in V, then V is complete. So the setup is as follows. We have a normed vector space V and W is a dense subspace. If every Cauchy sequence in W has a limit not necessarily in W but in V, then V is actually complete. Okay, so the proof is again not so difficult. Let Xn in V be a Cauchy sequence. We have to show that this sequence has a limit in V. Now, because W is dense in V, we can find a Cauchy sequence Wn in W such that norm of Wn minus Vn is less than 1 by n. Okay. Now, if you want to show that, okay, just a second, I sort of made a slight mistake. Let's just call this Vn for convenience, because I have used Vn later. In the beginning I said Xn, so that makes no sense. Okay, so if you want to show that Vn is convergent, we use the fact that whenever you have a Cauchy sequence in W, it converges. So what we are trying to do is we are trying to construct a Cauchy sequence Wn in W, which would converge to the same point that Vn would converge to. But Wn must necessarily converge, therefore Vn must also converge. That's the basic logic. Okay. Now, to do this, we have to first claim Wn is also Cauchy. Okay. Now, how do you see this? Well, fix epsilon greater than 0. Choose capital N so large that norm Vn minus Vm is less than epsilon for all n comma m greater than capital N. This is of course possible because Vn is a Cauchy sequence. Increase n to ensure 1 by n is also less than epsilon. Okay. Then observe that norm Wn minus Wm is by the triangle inequality less than Vn minus Wn plus Vm minus Wm plus Vn minus Vm. So this is the 3 epsilon trick which we have done so many times, and this is going to be less than or equal to 3 epsilon if n comma m is greater than n. In fact, this is going to be less than. There's no need to write less than or equal to. Okay. So this proves that Wn is a Cauchy sequence. So suppose Wn converges to V in V. By hypothesis, there will be an element in V that converge, that is the limit of Wn. Now the claim is that Vn also converges to V. This is the claim. Okay. So again, fix epsilon greater than 0 and choose n so large that if small n is greater than n, then norm Wn minus V is less than epsilon and norm Wn minus Vn is less than epsilon. Okay. Then it is immediate that norm Wn minus norm Vn minus V would be less than or equal to norm Vn minus Wn plus norm Wn minus V will be less than 2 epsilon. Okay. So this completes the proof. Okay. So what we have shown is the following. We have shown that if you start with a vector space V and you have a dense subset W, dense subspace W, such that every Cauchy sequence in W has a limit in V, then V itself is complete. Now final exercise for you. Show that this V bar is complete. And that will conclude the sketch of the proof that you can always complete a normed vector space. You can put it inside a larger normed vector space which is complete. Not only that, once you solve this exercise, you will realize that this f of V is actually dense in V. So that essentially shows that you can embed any normed vector space as a dense subspace of a complete normed vector space. Now I'm going to finish this video by one more theorem that is very useful in applications. Okay, so what it says is the following. This is essentially about extension of linear maps to the completion. Let V be a normed vector space, and let W be a Banach space. Okay, denote the completion of V by V bar. Okay, then any bounded linear map L from V to W can be extended to a linear map from a bounded linear map, of course, can be extended to a bounded linear map from V bar to W. Okay, if you start with the linear map from V to W, it extends to the completion. So first of all, before we even begin the proof, we have to understand what does it mean that L extends. Well, since f of V is a subspace of W, we just identify V and f of V, because anyway, so I must recall f is the map from V to V bar that we studied before. So since f of V is a subspace of not W, is a subspace of V bar, we identify V and FV and consider L to be defined from f of V to W. Okay, bounded linear. So there is a bit of unwinding to do, and it's better that you do it by yourself rather than me explaining what is happening. There's nothing deep going on, but it might seem a bit confusing because we are starting off with the map L from V to W. Now I'm just saying that identify this isometric embedding of V inside V bar, f of V with V, and treat L as a map from f of V to W. Okay, so what the claim is that if you start with this map L from f of V to W, you can get a map L tilde from V bar to W. That's the claim, bounded linear extension. It's a bounded linear extension. Okay, now how are we going to show this? Well, this L tilde exists. L tilde exists because of the previous exercise. You already know that f of V closure is going to be V bar. That's one. And L is uniformly continuous. All bounded linear maps are uniformly continuous. That we established previously when we studied the continuity of linear mappings between normed vector spaces. Because L is uniformly continuous and the fact that f of V closure is nothing but V bar, note here it's the closure, okay, and here it's just a notation. Since f of V closure is nothing but V bar and L is uniformly continuous, and uniformly continuous mappings extend continuously to the closure. Okay, so we have this map. L bar from V bar to W. Note, this is the place where we use the fact that W is a Banach space. So we get a continuous linear extension L tilde from V bar to W. The only thing that remains to be shown is that this L tilde is actually linear, and that's rather straightforward. So suppose x comma y are elements of V bar, okay, and xn converges to x and yn converges to y, where xn and yn are coming from they are coming from V, okay, which I am identifying with f of v tacitly. Okay, so take 2 points x comma y in the completion V bar and consider sequences xn converging to x and yn converging to y, where xn and yn are coming from V, which, let me just for clarity's sake just identify it already with f of v. Okay, then xn plus yn converges to x plus y. This is obviously. Okay, now what we have to do is to show that L of xn plus yn converges to L tilde of x plus y. Okay, this is also obvious. We also have L of xn plus yn converges to L tilde of x plus y. Obviously, this follows from the very fact that L tilde is an extension and it's a continuous extension, and since xn plus yn converges to x plus y, L of xn plus yn must converge to L tilde of x plus y. Okay, now similarly we have L of xn converges to L tilde of x and L of yn converges to L tilde of y. This is again by the fact that L tilde is a continuous linear extension. Putting all this together, we get that L tilde of x plus y is equal to L tilde of x plus L tilde of y. This is because L is linear, so this part L of xn plus yn is just L of xn plus L of yn. Okay, so this concludes the fact that L tilde of x plus y is L tilde of x plus L tilde of y. So we have essentially exploited the linearity of the map L on the space f of v and somehow translated to L tilde by passing to limits. Similarly, you can show that L tilde of cx is c L tilde of x, exactly in the same way. This will prove that this extension L tilde is linear. It's already continuous from the fact that we got L tilde by using a continuous extension theorem that we saw in a previous video. So this was a somewhat longer module, but work on it. It's not that difficult. It consists of a number of trivial checks that I have left for you intentionally so that you will have a deeper understanding of what is happening. So the moral of the story is, you have, for a given norm vector space, you always have a completion, and all linear maps to Banach spaces from the norm vector space extend to be bounded linear maps in the completion also. This is a course on real analysis, and you have just watched the video on the completion of a normed vector space.